Welcome to Part 3 in the series, Fundamentals of CR Basic Programming. In this video, I will demonstrate how to modify a template program to measure a sensor and store data in a complete program. Remember that often the easiest way to create a program in CR Basic is to use the shortcut Program Generator. But another simple way to create a CR Basic program is to start with a template program. When CR Basic is opened, select the data logger type. Select the CR1000X for this exercise. The template program contains all the commonly used components of a program, eliminating the need to recreate these components when writing a new program. In this exercise, I will start with the CR1000X default template program and modify it to make a thermocouple measurement. Campbell Scientific ships a Type T thermocouple with our data loggers because it's an easy-to-use sensor to get started with in CR Basic or Shortcut. The first modification to make is to add comments about what this program is used for. Comments are useful reminders when reviewing the program at a later date. Comments are also helpful if more than one person will be using or editing the program. It is also a good idea to include sensor wiring information at the top of a program. Type T thermocouples have two blue wires, one of which has a red stripe. The wire with the red stripe always goes to the low terminal of a differential channel. I will use differential channel 2 for this measurement, so the solid blue wire will go to 2H and the wire with the red stripe will go to 2L. This program will measure a Type T thermocouple once every second. The program will also save to a data table the average thermocouple temperature and a sample of the data logger panel temperature once per minute. Before I proceed with the program, I'll review how a measurement is made with a thermocouple. A thermocouple is a simple sensor that measures temperature. It consists of two dissimilar metals that are joined together at one end. A difference in temperature between the joined and unjoined ends creates a very small voltage. If I know the temperature at the unjoined ends, which are connected to the data logger wiring panel, then the data logger can calculate the temperature at the joined ends. For this reason, to make a meaningful thermocouple measurement, I need to know the temperature of the data logger wiring panel. A CR1000X data logger has a panel temp instruction used to measure the temperature of a data logger wiring panel, which makes a convenient reference for a thermocouple measurement. Therefore, in my program, I will add instructions to measure the wiring panel temperature and a thermocouple temperature. The template program has two default public variables, ptemp and batvolt. These variables are used to store the data logger panel temperature and battery voltage, which are both good indicators of data logger physical condition. For conciseness, I will delete the batvolt variable because I will not measure the battery in this program. Next, I will add a new public variable to store the thermocouple measurement. I will call this variable airTemp. It's a good idea to give variables meaningful names. I will use the ptemp variable to store the data logger wiring panel temperature, which I will use as a reference temperature for the thermocouple measurement. Ptemp is not very descriptive, so for clarity, I will change the variable name to panel temp. But now I see there's a problem with this name. When text turns bright blue, it means the text is a reserved keyword in CR Basic. In this case, the word panel temp is the name of an instruction. Keywords should not be used as variable names because that can lead to unexpected results. So I will change the name to panelTemp-C, which is valid. Notice variable names are shown in italics, so it's easy to differentiate them from other words or code in the program. For additional clarity, I will add some comments to describe what these variables are used for. For panelTemp-C, I will add the comment, panel temperature of the data logger, and for airTemp, I will add the comment, temperature of Type T thermocouple. Now that I have program variables defined, I will modify the default data table. I'm going to change the name of this table from test to 1min. Next, I need to change the time in the data interval instruction. An easy way to do this is to either right-click or press F2 while the cursor is on the data table instruction. This will open a parameter box where I can make edits. I'm going to change the interval from 1 to 60 seconds. I could also choose 1min if I want. Since I will not measure battery voltage in this exercise, I will delete the minimum instruction. Instead, I will add an average instruction and press F2 to open the parameter dialog box. In the dialog box, if I right-click in the source box, a list of declared public variables will pop up and I can choose the correct variable from the list. This is nice because I don't have to remember exactly how I spell the variable name. I can just select the right variable from the list. In part 2 of this video series, I discussed data types and when to use each data type. For this thermocouple measurement, I'm going to leave the data type parameter at FP2, because thermocouples are not very precise and I will not lose any precision by using FP2, which is a 2-byte floating point value. Next, I will add a sample instruction to measure the data logger panel temperature at the top of each minute. Note that the variable name in the source parameter is black, which means the name is not recognized as a variable. That's because I changed the variable name from ptemp to paneltemp_c at the top of my program. So I need to change it here, too. If I right-click on the name, I will get a pop-up list of variables, which makes it easy to select the right one. Or I can type it in if I prefer. Now that I have set all my variables in data tables, I will work on the main program. All instructions for the main program fall between begin_prog and end_prog, which designate the beginning and end of a program. A program cannot compile without these two statements. Within the begin_prog and end_prog block, there's usually a scan next scan block, which tells the data logger how often to execute the code within the block. In this exercise, I will make two measurements, a panel temp measurement and a thermocouple measurement. Since I don't need the battery measurement, I will delete it. Let's look at the panel temp instruction. To bring up the help for an instruction, put the cursor anywhere in the keyboard and press F1. The help says the panel temp instruction is used to read the temperature of the data logger wiring panel and output the value in degrees Celsius. It also says the measurement from the panel temp instruction can be used as the reference temperature for thermocouple measurements. But in my program, I need to modify the ptemp instruction to use the correct destination variable. To choose the correct variable, right-click on the text currently in the dest parameter and choose the correct variable from the pop-up list of variables. Or, type in the variable name directly. I will use the drop-down list of variables and choose the paneltemp_c variable I declared earlier. The second parameter in the ptemp instruction is fn1, or fnotch. This fnotch parameter is used in newer data loggers like the CR1000X and CR6. Older data loggers, like the CR1000 or CR800, use a similar parameter called integration time. The fnotch and integration parameters effectively do the same thing. They are just expressed differently. Fnotch is expressed in hertz, and integration is expressed in microseconds or milliseconds. Both fnotch and integration are used to reject ambient electrical noise in the measurement environment. Lower fnotch frequencies take more measurement time, but result in cleaner, less noisy measurements. So, if fast measurements aren't needed, it's a good idea to choose a lower fnotch to filter out as much noise as possible. Since I'm in North America, the best fnotch to reduce noise is 60 Hz, because the AC power lines in North America deliver power at 60 Hz. Power lines result in a lot of electrical noise, so I will get a cleaner measurement if I can filter out that noise. In Europe, it's best to use an fnotch of 50 Hz, since European AC power lines deliver power at 50 Hz. If fast measurements are needed, then choose a faster frequency, like 15,000 Hz, or even set that higher if needed, up to 31.25 kHz. Just know that there's a trade-off between speed and noise filtering. Now I'm ready to set up a thermocouple measurement. I'm going to put the cursor where I want to place the instruction in my program, and then look in the instruction panel to find the right instruction to measure a thermocouple. Since the thermocouple measurement relies on the panel temperature measurement, I want my thermocouple measurement instruction to immediately follow my panel temperature measurement instruction. In the instruction panel, there's a long list of instructions. I can narrow this list down by choosing the measurements category from the drop-down list, but there are still a lot of options. If I'm not sure which one to use, I can use the search or index options in the help to help me find the correct instruction. For example, I can go to search and type in thermocouple. This puts the instructions related to thermocouples at the top of the list. I see similar results if I search for thermocouple in the Index tab. I am not using a CDM, and I will choose a differential channel for this measurement. So I will choose TC_diff from this list. TC is for thermocouple, and diff is for differential channel. When I click Insert, a parameter dialog box opens. TC_diff has a lot of parameters, but I can leave most of them at their default values. Destination is where I want to store the measurement, and that will be my air temp variable. Reps is used to indicate how many sensors to measure with a single instruction. In this case, I'll leave the reps at 1. For voltage range, I want to use the smallest available voltage range, which is 200 millivolts, because thermocouples output a very small voltage. The defaults for parameters are usually set to the option most commonly used by customers. Notice that there are 2 options for MV200, one with a C and one without. The C option checks for an open connection of a bad sensor by first applying a short test voltage to the analog channel. It will result in a measurement over range, or NAN, if there's a problem. The advantage of using the C option is that it clearly indicates if there's a sensor problem, instead of returning a floating point value. The trade-off is that the C option increases the time it takes to make the measurement. Consequently, this increases the time for the data logger to execute its program and may cause issues with slow responding sensors because of the time it takes them to recover from the test voltage. For this exercise, I will leave this at MV200C. For the diff-chan parameter, I need to choose the channel my thermocouple is connected to. At the beginning of the program, I made a note that the thermocouple is connected to 2H and 2L, which is differential channel 2, so I will choose 2 here. For TC type, I will choose type T because that is the type of thermocouple I have. Tempref is the reference temperature, which in this case will be the panel temp measurement stored in the panel temp C variable. The other parameters in this instruction have common default values, so I will leave those alone for now. Now, I have my 2 measurement instructions and I'm almost done with my program. In an earlier video, I talked about data tables and demonstrated that every table in a program needs a corresponding call table instruction telling the data logger to write data to that table. If I try to compile my program right now, I will get an error saying that data table test is not found, and that's because I changed the name of the table in the default template from test to 1min. So, I need to change the table name in the call table instruction to 1min. It's easy to find data table names by right-clicking on the name of the call table instruction. This pops up a list of tables in the program. I will choose the 1min table. So in this program, the data logger will measure its wiring panel temperature and a thermocouple on differential channel 2 once a second. And internally, the data logger will do a calculation with these measurements to convert the thermocouple output from a voltage to a temperature in Celsius. If the default output for an instruction is unknown, look in the help for that instruction and it will give the form of the default output value. I'm going to leave the TC diff multiplier at 1 and the offset at 0, so the output will be in Celsius. If I wanted the output to be in Fahrenheit, I could change the multiplier to 1.8 and the offset to 32. Next, I will compile the program and save it as thermocouple.cr1x. Now I will send this program to the data logger. Before I send the program, I will collect data so I don't lose the data that's currently stored on the data logger. In the Monitor Data tab, I see the public table and the 1min table. New records will be written to the 1min table at the top of each minute, and the public table displays real-time 1-second measurements. If I heat the end of the thermocouple, I see the air temp value increase. If the temperature goes down when the thermocouple is heated, it indicates the thermocouple is wired backwards. Make sure that the wire with the red stripe is attached to 2L. In the 1min table, I see the average air temp, which in this case is an average of 61 second measurements. Now I have a complete functioning CR Basic program that is storing air temperature and the data logger wiring panel temperature in my data logger. In future videos, more CR Basic programming topics will be discussed. If you have any questions about CR Basic programming, refer back to this video series, read the CR Basic help files, or contact a Campbell Scientific representative who will be happy to assist you.